Far out in Virgo, two blazing suns orbit so close that gravity stretches them into teardrops and bends the space around them. Tonight's journey drifts into that warped starlight, slowing down every orbit, every ripple of heat until it all becomes a soft cosmic lullaby. If this kind of science storytelling helps you relax, please remember to gently tap like and subscribe so more deep space sleep journeys can find you. Now take a slow breath and let Spica carry you into the dark. In a quiet patch of the Virgo constellation, a single bright point hides a more complex structure. Two massive blue-white stars orbit so close together that gravity reshapes their surfaces and their light. From a distance, the system looks simple and steady, yet inside that point, motion and distortion never stop. The pair forms a close binary, a double-star system in which both members share a tight gravitational bond. Each star circles the shared center of mass and traces a small loop in space while their combined glow spills outward as one blended beam. At this distance, the two orbits overlap in appearance, so the light seems to come from one stable location rather than from two moving sources. The separation between them is small compared with the overall size of the orbit, and their silhouettes almost touch in every rotation. Gravity in this regime acts like a short, invisible rod that never quite lets them drift apart. The scene can be imagined as two drops of molten metal on a smooth plate drawn toward each other by surface tension yet held in balance before merging. Their outer layers are not solid crusts but hot plasma that responds quickly to small differences in force. Each star becomes slightly elongated along the line joining their centers and stretches into a form that is closer to an ellipsoid than a perfect sphere. The side facing the companion stands under stronger pull, while the far side experiences weaker pull, and the whole structure adjusts continuously. At any moment there is a subtle gradient in surface gravity from one point to another, and temperature follows that gradient with small but important shifts. The hottest regions concentrate where material is compressed most strongly, while cooler areas gather where the pull is weaker and the surface can swell outward. Light behaves as a tracer of these conditions and leaves bright bands and softer zones that sweep across space as the stars rotate. A slow mental camera can track one bright arc moving around the distorted rim of a star, like a band of slightly thicker metal that glints on a rotating uneven ring. This constant rearrangement creates a natural pattern of variation in the intensity that escapes into space, even when the total emitted energy remains roughly stable. The system does not flicker violently yet. Over time, its brightness curve carries the imprint of shape and rotation. In this context, the orbit itself is compact and rapid, with a period of about 4 days, which is similar to a short week on Earth, compressed into one smooth repeating cycle. During that time, each star completes a full circuit around the shared center and stays in close company with its partner. Their speeds are high in absolute terms, and each star moves many tens of kilometers every second along its track, yet the motion unfolds in a steady and almost hypnotic pattern. Intuition tends to expect such speed to produce clear separation, but at the distance of Earth the angular change remains too small for the pair to split under ordinary viewing. Vision meets a limit of resolution that is set by the wave nature of light and by the scale of any opening that gathers that light. Beyond that limit, two separate luminous bodies merge into one apparent point, and the internal motion disappears into a single stable spark. Only indirect signs can reveal that the system is double, and the first such sign lies in the way the shapes must react to shared gravity. The continual distortion means that no fixed, rigid surface exists in the outer layers. Instead, there is a zone where gas behaves like a rounded but flowing envelope that must always balance pressure against gravity. Near the narrow region between the stars, the equipotential surfaces crowd together and form a kind of gravitational neck, where material would feel the tug of both bodies almost equally. In a visualization, that neck can appear as a softly pinched bridge between two glowing lobes that is slightly dimmer than the main faces, yet still bright against the surrounding dark. Farther out, the combined gravitational field starts to resemble that of a single mass, and the inner details of the orbit become harder to sense. This shift from local complexity to distant simplicity marks another limit of intuition, where many moving parts reduce to one effective source. On small scales near each stellar surface, curvature in both geometry and potential remains strong, and even small changes in position lead to strong differences in force. On large scales, the binary behaves like one luminous beacon that is steady enough to anchor the surrounding pattern of fainter stars. The contrast between those scales gives the system a quiet kind of drama in which extreme heat speed and distortion remain hidden behind apparent calm. Inside the bright point in Virgo, gravity sculpts two hot stars again and again, while from afar the pair settles into the role of a single guiding light. That gentle difference between inner motion and outer stillness prepares the way for a closer look at how light from such a distorted surface is measured and interpreted in the next part of the journey. Orbit inside this binary system follows rules that are both simple and strange. Two massive stars move along a shared oval path where speed and distance trade places in a repeating cycle. The orbit is not a perfect circle, but a slightly stretched loop with a closer side and a farther side along the track. At the nearest point, gravity between the stars is strongest, and their motion bends sharply around the shared centre of mass. Farther along the orbit, each star swings out to a slightly greater distance where the pull is weaker and the curve looks wider and smoother. The path in space resembles two lanes on a small running track that loop endlessly around a quiet central point. Each star keeps to one lane, yet the lanes remain close enough that the distance between them never grows large. In this configuration, gravity and motion together act like an elastic connection that tightens and relaxes in a regular sequence. When the stars draw close, the pull accelerates them and they rush through the tight turn. When they swing out, the same motion carries them more slowly through the wide section, where gravity has less leverage. A simple rule guides this behaviour. It comes from conservation of angular momentum. That rule states that orbital motion adjusts when distance changes so that the overall rotational budget stays constant. The idea can be pictured through a toy with two heavy weights on a short string. The system spins faster when the weights move inward. It spins slower when they move outward. In the binary system, no solid arms exist, but the same trade between speed and distance still holds as an invisible constraint. At the scale of the orbit, this relationship means that one part of the path is crossed quickly, while another part is crossed more gently. Light behaves as a record of that timing, because changes in motion modify the way radiation is emitted from different parts of the surfaces. One characteristic number helps anchor the sense of size. The separation between the stars remains on the order of tens of millions of kilometers. That span is comparable to the distance between a planet and its star in the inner region of a typical planetary system. At this range, the two stellar disks almost overlap from certain angles. Any small change in position can significantly alter which regions of the distorted surfaces face outward. The visual anchor becomes a narrow racetrack drawn on a dark floor where two small lamps glide along opposite lanes. Their beams illuminate different sections of the outline as they move. Near the closer end of the track, the lamps sweep past each other quickly, and the light along the inner boundary brightens for a short moment. Along the wider arc, their relative motion slows, and the focus of illumination drifts more gradually over the outer boundary. Even though this picture offers a useful guide, intuition meets a limit when trying to follow two frames at once. One frame tracks the motion of each star around the shared centre of mass. Another frame tries to watch from the perspective of one star alone. In that moving frame, the companion seems to describe a more complicated shape that does not match simple circular motion. Coordinates in the mind become tangled between the two viewpoints, and the neat geometry of the orbit loses clarity. This confusion marks a limit of intuitive understanding that appears whenever several moving reference frames overlap. In practice, the cleanest description chooses the frame of the shared centre of mass and lets both stars follow clean loops in that reference. From that vantage, the pattern returns to a pair of steady ovals whose positions and speeds remain predictable at every point. A signal would trace these loops by sampling the gravitational pull over many cycles. It would also track the direction of light and average the results to smooth away momentary fluctuations. On small scales near each stellar surface, the path of the orbit cuts close enough that tidal forces can raise and shift bulges of plasma. Motion at that level looks like slow extensions and compressions of the outer layers in response to the changing direction of pull. Over much larger scales, the orbit shrinks to a single tiny ring inside the broader picture of the Virgo constellation. On an even larger view, it sits far inside the disk of the galaxy. That scale shift from tight racetrack to faint ring inside a spiral system underscores how local and contained this rapid motion remains. Within its own frame, the binary feels dynamic and intense, while against the background of the galaxy, it becomes one modest repeating pattern among many. At this distance, the orbit may be tilted relative to the line of sight. In that case, the ovals project into shorter or longer apparent paths on the sky. If the plane lies almost edge on one star, sometimes passes in front of the other. Their combined light then follows a smooth dip and rise. If the plane lies closer to face on each star, remains beside the other in projection. In that geometry, the motion shows itself more clearly through changing speed rather than through overlapping disks. In both cases, geometry decides how much of the underlying dance is visible and how much is hidden inside the point-like appearance. Observation meets another limit here, because only certain orientations produce strong and repetitive brightness changes, while others keep the curve almost flat. Information about the orbit then depends on subtle variations in timing and colour that must be followed slowly over many cycles. At the theoretical level, equations of motion can describe the path exactly for two-point masses. Real stars are extended bodies with distorted shape. Their mutual tides mean that each star reacts not only to the overall pull, but also to variations in that pull across its own diameter. That small correction gradually alters the orbit and spreads energy between rotation and orbital motion. Over long spans of time amounting to millions of years, the tidy oval may slowly evolve. On shorter astronomical timescales, it remains effectively steady. The orbital pattern in the present era therefore offers a stable framework. On that framework, more detailed effects can ride, and the behaviour of light from Spica can be interpreted in the next stage of the exploration. The colour of Spica in the sky appears simple and cool, yet that soft blue tint reflects an extreme level of heat. Surface temperature shapes the nature of each star in the pair and controls how their combined light spills across space. In physical terms, these are hot main sequence stars with surface layers heated to tens of thousands of degrees. One representative figure is about 20,000 degrees at the outer layers, which is more than 3 times the surface temperature of a star like the Sun. The comparison is easier to picture as a fire, where ordinary orange flames stand beside a rare white core that glows with sharper intensity. At this distance, the human eye would register mainly hue and brightness, yet the radiation spreading outward encodes a full thermal story. Light behaves as the visible skin of internal energy that has climbed outward from much deeper regions. In each star, energy arises in a compact core and travels outward through layers of plasma before it can escape. The region where light finally leaves without being scattered many times is called the photosphere. The photosphere is a thin shell where the star changes from mostly opaque to mostly transparent in a short vertical range. In the binary system, this shell does not sit on a perfect sphere. It wraps around a stretched and rotating body and follows the distorted gravity field discussed earlier. Gravity is slightly stronger in some regions and slightly weaker in others. That difference modifies how tightly material is held and how much it can expand. In stronger gravity regions, the surface lies deeper in the atmosphere where temperatures run higher. In weaker regions, the surface sits in higher, cooler gas. The result is a pattern known as gravity darkening, where hotter, brighter zones cluster near the tighter poles and cooler, dimmer bands spread around the swollen equator. A mental camera can fly low over one star and watch the surface shift gradually from intense pale white blue near the rounded poles to a slightly softer steel blue around the midsection. No sharp boundary appears. Instead, there is a gentle gradient in colour and intensity like a heated ceramic plate whose centre glows nearly white while its stretched rim holds a deeper shade. This pattern becomes more pronounced because the stars rotate quickly as they orbit. Rapid rotation flattens the poles and broadens the equator. The shape then reinforces the differences in surface gravity and temperature, so the brighter polar caps look like two small lantern crowns, while the equatorial belt becomes a dimmer band pulled around the middle. The main concepts here are simple yet powerful. Effective temperature gives the single value that best describes the overall glow of a star. Gravity darkening explains how that temperature spreads unevenly across a distorted surface. Together they set the brightness map that distant observers would reconstruct from careful study. However, direct sensing meets a clear limit. No thermometer can touch the photosphere, and no image can resolve the tiny shapes of the stars from a remote vantage. The apparent disk of each member spans far less than a single pixel in any ordinary image. Observation must instead rely on the colour balance of the light and on fine structures in the spectrum that reveal which atoms are present and how strongly they are ionized. Certain lines fade or strengthen as temperature rises, and those changes act like marks on a hidden scale. For a close binary, there is an additional difficulty. Light from both stars blends together before it can be measured, and only subtle shifts in wavelength as the stars move can separate their contributions. At this point, intuition may struggle because the mind tends to imagine a clearly drawn, glowing ball rather than a region defined by probabilities of photon escape and overlapping sources. The photosphere is not a solid crust. It is a depth range where the chance of a photon leaving the star without another interaction finally becomes high. That concept belongs to radiative transfer. Radiative transfer is the process by which light diffuses outward through matter until it escapes into space. In a calm analogy, it resembles fog that slowly thins as a path moves outward until the air finally becomes clear. The difference in a star is that the fog is glowing on its own rather than lit from outside. In the binary system, this glowing fog layer follows the stretched outline of both stars and responds to tidal forces and rotation. On small scales, the atmosphere may host waves of compressed gas that slightly adjust local temperature and brightness over time. On large scales, the stars behave like two stable blue beacons whose total output remains almost constant over many orbits. The scale shift from local patch to entire star and then to full system helps place the complexity in context. A tiny region on the equator may change temperature slightly, while the global luminosity changes only by a modest amount. Yet those modest changes can still leave faint patterns in the combined light curve that patient analysis can recover. The heat carried by the radiation field also pushes outward against gravity and helps decide the overall radius of each star. In these hot stars, radiation pressure is no longer a small correction, but a significant part of the support against collapse. That extra support allows their envelopes to spread somewhat farther than cooler stars of similar mass. The balance between gravity and radiation then fixes both the size and temperature of the photosphere. Within that balance, the gravitational interaction with the companion adds further subtle shifts. Over very long timescales, the intense radiation field will drive winds that peel away material and carry mass out into space, where it joins the interstellar medium. On the timescales relevant for the current orbit, the temperature pattern stays stable enough to serve as a reference. In later stages of the journey through this system, that reference map of heat and brightness will link naturally to the way spectral lines move and change as the two stars swing around each other in their tight gravitational embrace. In a compact binary like Spica, gravity does more than hold the stars in orbit. It carves a shared landscape of invisible basins where material prefers to stay. Each star sits inside its own gravitational hollow, a three-dimensional well dug into the fabric of space around the pair. Near the center of a well, the pull points inward almost equally from all directions. Farther out, the shape of the well becomes skewed by the presence of the companion and by the overall orbital motion. A useful picture treats the gravitational and rotational effects together as a single effective potential that acts like a smooth landscape. In that landscape, the stars occupy neighbouring valleys separated by a low pass. A Roche lobe is the region where one star keeps its material. In the combined landscape of the binary, each Roche lobe traces out the deepest part of one valley, wrapped around the star like a distorted shell. The lobes meet at a narrow saddle point where a small change in position could send material toward either star. The main number that fixes intuition here is the size of the lobes. For a system like Spica, each lobe extends to several times the radius of the Sun, so each star occupies a volume that would dwarf the familiar solar disk. If the Sun were imagined as a small pebble, one of these stars would resemble a boulder beside it, and the surrounding lobe would fill a larger rounded cavity. The primary visual anchor becomes a cross-section through two neighbouring valleys carved into a smooth hillside. In this picture, thick liquid rests in each hollow. The liquid fills the first bowl around one star, and the second bowl around the other star. Between the bowls, a shallow saddle connects them raised just high enough that only the very top layer comes close to spilling across. In reality, the liquid is a hot plasma envelope held by gravity, and the hillside is the effective potential surface. At this distance, an individual parcel of gas near the stellar surface feels a gentle tug that reflects its position in that landscape. Inside the lobe, the net pull guides it back toward the host star. Near the saddle, the pull from both stars almost balances, and even a small push can make it drift one way or the other. These tidal forces do not act as sudden jerks. They work continuously and reshuffle the outer layers in a slow, steady way. Tidal force is the difference in gravitational pull between one side of an object and the other side. A simple example appears when considering how gravity is slightly stronger on the near side of a body than on the far side. In the binary, this difference stretches each star along the line that joins their centres and compresses it slightly in the perpendicular directions. The outer gas responds by sliding into a shape that fits the lobe, creating an elongated teardrop rather than a clean sphere. Surface layers near the pointed end of that teardrop lie closer to the saddle region. Layers as near the rounded back feel a cleaner pull toward the host star and sit deeper in the valley. Light behaves as a tracer of these differences. Where gas sits deeper in the potential well, the surface lies closer to hot inner layers and radiates more intensely. Where gas lies nearer the saddle, the surface reaches slightly cooler heights and glows a little less strongly. A slow mental camera can sweep around one star and watch the teardrop outline glide past with the pointed nose always facing the companion and the rounded back trailing behind. Intuition, however, meets a limit when trying to picture the full three-dimensional structure. It is easy to imagine a two-dimensional valley or bowl. Extending that picture into 3 dimensions with nested lobes and saddles is harder. Observation faces a similar limit. No direct image resolves the surfaces of Spica or maps the shape of its lobes. Instead, models must infer the structure from orbit parameters and from how brightness and colour change with phase. The effective potential is calculated rather than seen, and the lobes appear first as contours on a diagram. A signal would move through this gravitational landscape by following the easiest descent paths toward one star or the other. From a small-scale viewpoint near the surface, the controlling details are local. A parcel of gas feels the gradient of gravity over distances comparable to the stellar radius. From a much larger viewpoint spanning the entire orbit, the 2 teardrop lobes shrink into compact regions inside one wider trough that belongs to the whole system. That scale shift from local valley to global basin helps clarify why the binary behaves like a single attractor at large distances. Any object far away responds mainly to the combined mass and hardly notices the fine structure of the lobes. Only close in does the double valley layout become important, and only then do choices between the 2 stars matter. Over long times, this sculpted potential shapes how mass could someday move between the stars or leak away into space. In the present era, it mainly fixes the outline of each star and sets the stage for how internal tides will move energy and angular momentum through their interiors. The calm balance of these basins provides a quiet background against which more dynamic processes like waves of compression and subtle shifts in rotation can play out in the sections that follow. Brightness from the Spica system looks calm at first glance. In reality, the light rises and falls in a smooth pattern as the distorted stars rotate in orbit. The changes are not sharp flashes. They are gentle swells and dips that repeat with the orbital period. This pattern is called a light curve. A light curve is a record of brightness measured over time and plotted as a smooth line. For a close binary with stretched stars, the curve carries the imprint of shape and viewing angle, even when no eclipse occurs. To picture this effect, it helps to imagine a large globe made of frosted glass with pale and darker paint gently brushed across its surface. The globe turns under a fixed lamp, and its apparent brightness changes as different regions move into view. In the real system, the stars act like those turning globes, except that the patterns come from gravity darkening and from how the elongated figures present their broad or narrow sides to the line of sight. One key number gives a sense of scale for the variation. The total brightness may change by only a few parts in 100 during one orbit, similar to watching a room that grows slightly dimmer and brighter as thin curtains shift in a light breeze. On short timescales, the change at any one moment is very small. Over the span of days, the rhythm becomes clear. When the long axis of each star lines up sideways to the observer, the projected area is largest and brightness rises. When the narrow end points more toward the observer, the projected area shrinks and brightness falls. Light behaves as a quiet reporter of geometry, using no sudden moves, only slow modulation. The physical detail behind this lies in the way the surface of each star radiates across its disk. Limb darkening plays an important role. Limb darkening is the tendency for the edge of a stellar disk to appear dimmer than the centre. It happens because lines of sight near the centre reach deeper, hotter layers, while lines near the edge travel through cooler outer material. A simple earthly analogy compares this to looking into a cloudy liquid, where the centre of the container lets vision reach deeper and appear brighter, while near the rim the line of sight stays in shallower, cooler layers that look more muted. In a distorted star, the centre and limb are no longer arranged on a perfect circle. The elongated shape means that some directions present a broader, bright centre, while others give a smaller one. The combined effect of ellipsoidal shape gravity darkening and limb darkening therefore sculpts the exact form of the light curve. A mental camera can hold a long exposure of one full orbit and watch brightness rise twice and fall twice as the stars trade orientations. The curve resembles a smooth double wave drawn in soft ink across a calm strip of paper. Intuition expects that such a dramatic object would change brightness by a large amount. Here that intuition meets a limit. The stars are huge and intensely luminous, so even a modest fractional change involves a great deal of energy. Yet from far away the relative difference remains small. Instruments must measure the light with high precision to uncover a pattern that the unaided eye would miss. Observation also faces a resolution limit in time. If measurements are too widely spaced in the orbital cycle, the smooth wave becomes hard to reconstruct and seems like random scatter. Once the sampling becomes regular and fine enough, the underlying rhythm appears. A signal would trace this rhythm by recording brightness at steady intervals for many weeks, then folding the data onto a single orbital period. Folding a light curve in this way means stacking several cycles together to improve clarity. As the star pair continues its motion, the depth and shape of the curve stay almost the same. Small departures can hint at additional structures, such as surface spots or pulsations, but in a hot system like Spica, the main contributor remains geometric. On small spatial scales near each patch of photosphere, the emission depends on local temperature and angle. On the larger scale of the entire stellar disk, those patches blend into one brightness value for each star at each moment. On the larger scale of the whole system, that brightness combines into a single value for the pair. The scale shift from patch to disk to system shows why simple models can still describe the curve. Many details average out, leaving only the bulk properties of shape orientation and darkening patterns to dominate. The continuous nature of the light curve also supports the idea that the stars do not carry large opaque structures that would cause sudden dips. Instead, the envelope appears smooth and stable on the timescale of the orbit. This steadiness is important because it allows precise comparison with theoretical curves generated from trial shapes and orbital parameters. When model and data align, the match confirms values for the inclination of the orbit, the degree of distortion, and the distribution of temperature across the surfaces. These parameters then feed back into the wider picture of the system, cross-checking masses and radii derived from other methods. The brightness pattern therefore acts like a long, faint barcode encoding geometric information in a form that instruments can read even when the stars remain unresolved points. Over much longer timescales extending to millions of years, slow changes in structure or orbit could alter the shape of the curve. In the present epoch, it serves as a stable heartbeat for the system. That quiet heartbeat provides the natural bridge to methods based on colour and wavelength, where the same motion and distortion leave their mark in the sliding of spectral lines and deepen our view into the dynamics of this close pair. In a system like Spica, motion that cannot be seen directly still leaves a steady mark in the spectrum of its light. Spectral lines shift in wavelength as each star moves toward and away from the line of sight. That motion turns the combined spectrum into a quiet record of the orbit. The method rests on the Doppler effect. The Doppler effect is the change in observed wavelength when a source moves along the direction of observation. A gentle analogy is the change in pitch of a distant siren that passes by. In the star, the shifting feature is a dark or bright line in a band of light. In the spectrum of a hot star, many narrow structures appear where specific atoms absorb or emit at preferred colours. These features act like markers painted onto a moving conveyor belt. As the stars complete each orbit, the conveyor of light slides slightly toward shorter wavelengths, and then toward longer wavelengths in a smooth cycle. A radial velocity curve records this motion over time. Radial velocity is the component of a star's speed along the line between it and the observer. For a close binary where both stars contribute light, two intertwined curves form in that plot. Each curve rises and falls as its star swings around the shared centre of mass. One characteristic number helps fix the sense of scale. Typical speeds along the line of sight reach about 100 kilometers every second. That speed is similar to circling a planet like Earth in less than a day. In the spectral image, this speed does not appear as a streak or blur. It shows up as a tiny displacement of each line compared with its rest position. The visual anchor becomes a long, narrow photographic strip with many dark bands running across it. Over time, the bands slide gently in opposite directions for the two stars, like two sets of tracks shifting on a slow-moving escalator. Light behaves as both messenger and clock in this picture. Every small shift in wavelength corresponds to a precise change in speed. Every crossing of the curves marks a moment when one star moves exactly sideways in the plane of the sky. At that moment, its radial velocity passes through zero. From these curves, the orbital period and the shape of the path can be measured. The ratio of their heights reveals the ratio of the stellar masses, yet the method meets clear limits. Spectrographs cannot separate features below a certain spacing, and noise from faint light blurs the finest structure. In a blended spectrum, lines from both stars can overlap and distort each other when their speeds bring their signatures close together. At such times, the neat picture of two clean conveyor belts begins to fail. Careful modelling is needed to untangle which part of the pattern belongs to which star. Intuition also reaches a boundary when confronted with the smallness of the shifts. The fraction of change in wavelength is tiny compared with the total spread of the spectrum. Without a firm mental anchor, those numbers can feel abstract and weightless. The conveyor belt image helps by focusing thought on relative displacement instead of absolute size. On small physical scales, the shifts arise from the behavior of individual atoms in the photosphere. Each atom absorbs light at a particular energy, and therefore at a particular wavelength. When the whole star moves, these absorption points march together to new wavelengths as a group. On the scale of one star, this motion reflects the orbital dynamics and the rotation already discussed. On the scale of the binary system, the two sets of lines weave around each other, and each set traces its own path through wavelength space. Farther out on the scale of the galaxy, the entire pattern rides along with the general galactic motion. That extra motion adds another layer of Doppler shift on top of the orbital one. The nested nature of these motions forms a gentle ladder of scales from local atomic transitions to the long sweep of galactic rotation. A signal would isolate the orbital part by tracking changes that repeat with the period known from the light curve. It would ignore shifts that remain constant over many cycles. There is also a limit tied to geometry. Only the component of motion along the line of sight contributes to the observed shift. If the orbit was seen exactly face-on, no radial velocity change would appear, even though the stars whirl rapidly around each other. In that case, the method would fall silent about masses and speeds. For Spica, the inclination is favourable enough that clear variations can be measured while the stars remain only partly aligned along the viewing direction. This intermediate angle allows mass estimates that are strong, but still carry some uncertainty linked to the exact tilt. With those caveats in mind, the paired radial velocity curves become powerful tools. Their amplitudes reveal how fast each star moves. The ratio of these amplitudes gives the ratio of the stellar masses. Combining this information with the orbital period and with distance estimates from other techniques allows the absolute masses to be set. The radii then follow on a secure scale. The process is quiet and repetitive. It resembles weighing two dancers on opposite sides of a large balance beam. In that picture, the beam shifts in response to their steps and rises and falls by different amounts and at different speeds. Over long periods, the curves remain stable and confirm that the basic architecture of the system does not change quickly. Small deviations may hint at subtle pulsations inside the stars or additional distant companions, but the dominant story stays simple and steady. Within the bright point of Spica, light itself functions as a moving ruler that records speed and mass and geometry without ever touching the stars. This spectral ruler prepares the way for a deeper look inside the stellar interiors. In those depths, pressure, waves, and internal structure leave their own slow signatures on both light and motion. Gravity around each star in Spica does more than pull on matter. It also shapes the flow of time and the paths that light can take near the surfaces. In strong fields, Newtonian pictures of force begin to give way to a gentler view, built from curved space-time. In that view, mass does not tug through empty space. Instead, mass reshapes the stage itself, and objects move along the easiest tracks on that curved stage. A helpful image uses a wide, dark sheet held under tension. When a heavy ring is placed on the sheet, the fabric sags into a smooth hollow around it. A second ring dropped nearby, settles into its own hollow, and both rings can circle each other along the curved slopes. In the Spica system, each star plays the role of one of those rings, while space-time takes the place of the stretched fabric. The hollows are shallow compared with those around denser objects like neutron stars, yet they are not negligible. Close to the photosphere, the escape speed reaches several hundred kilometers each second, comparable to crossing a large continent in just a few seconds. That speed marks how deep the gravitational hollow is. An object would need that much speed to climb out without falling back. Space-time curvature at this depth has two gentle yet important consequences. The first is a small deflection of light as it passes near the stars. The second is a slight shift in the ticking of any clock bound to their surfaces. Gravitational redshift is light losing energy while climbing from gravity. In everyday terms, that loss appears as a stretch in wavelength toward the red side of the spectrum. A calm analogy imagines a ball thrown upward inside thick honey that slowly drains its speed. The ball still escapes but moves more slowly. Likewise, a photon leaving a gravitational hollow keeps going yet carries slightly less energy. This effect matters because it subtly alters the exact positions and shapes of spectral lines. In a system like Spica, the redshift is small. It is much weaker than the shifts caused by orbital motion, yet it contributes a steady offset that does not change with phase. Careful models must include it when extracting precise temperatures and surface gravities from the spectra. Time dilation adds another delicate layer. Time dilation in gravity is slower ticking of clocks deeper in a gravitational field. Near the photosphere of a massive star, a perfect clock would run a tiny bit slower than an identical clock far away. The difference for Spica is minuscule. It amounts to far less than a billionth of a second over the span of one ordinary second. Over short human timescales, such a difference would be impossible to notice. Over millions of years, the integrated shift would still remain modest. Intuition struggles here because all direct experience comes from weak gravity, where such variations vanish into noise. There is also a clear observational limit. No physical clock can sit on the surface of Spica and send back its readings. The only way to sense time dilation is to trace its imprint on light and on orbital dynamics through models. At this point, the sheet image helps again. On the stretched fabric, the sag under each ring represents potential depth. Clocks nearer the centre of a sag tick more slowly. Clocks far out on the flat part tick faster. In the Spica binary, the sags overlap and the combined surface becomes slightly asymmetrical as the stars move. On small scales near one photosphere, the curvature determines how light cones tilt and how quickly signals can climb out. On the larger scale of the whole binary, that same curvature shapes the overall orbit and keeps each star bound to the other. On the still larger scale of the galaxy, both stars sink together into a far deeper yet broader gravitational basin dominated by the galactic mass. That scale shift from local dimples to global bowl highlights how the same underlying law covers many layers of structure. Light bending near Spica is far too weak to produce dramatic arcs or multiple images. It remains in the realm of slight corrections. The deflection mainly adjusts how beams from one star skim past the limb of the other, and how the combined brightness pattern forms at different phases. Observation meets limits again, because instruments cannot yet isolate these tiny angles in distant stellar systems. Instead, gravitational light bending enters through theory as a small term added to paths computed for photons leaving the stars. Even as a small term, it plays a conceptual role. It reminds that the same equations which explain more extreme phenomena also apply here in a gentle regime. A signal would experience this curvature as a slight change in travel time depending on its route through the gravitational hollow. A path that passes close to one star would take a little longer than a straight line in completely flat space, because space-time near the mass is stretched. That extra travel time is small yet real. In a sense, it acts like a faint echo of the deeper potential. Together, these pieces build a quieter understanding of the phrase gravitational field. Instead of a simple pull, there is a curved geometry that guides matter and light. For Spica, this geometry is not violent. It is a smooth depression around each star, joined into a shared basin for the pair. Over the long history of the system, this curved background influences how mass loss proceeds, how orbits might evolve, and how any future companions would move. In the present, the curvature simply holds the close binary in a stable embrace and slows time by only the slightest amount. That calm bending of space-time sets the context for the intense processes inside the stars themselves, where pressure waves and fusion reactions create the energy that later climbs through this curved arena to reach the wider galaxy. Beneath the bright distorted surfaces of Spica lies a layered interior that stays hidden, yet controls everything seen outside. Gravity and pressure balance each other through the whole volume and hold the stars in a steady shape even as they orbit and spin. This balance is called hydrostatic equilibrium. Hydrostatic equilibrium is the condition where inward pull from gravity is matched by outward push from pressure at every depth. In the core of each star, the pressure comes mainly from extremely hot gas and from radiation trapped in dense layers. One guiding number anchors the scale. Core temperatures reach tens of millions of degrees, roughly comparable to stacking millions of very hot industrial furnaces together into one compact region. At those temperatures, atomic nuclei move fast enough to overcome their mutual repulsion and fuse into heavier elements. Fusion is the source of energy that later climbs toward the surface as light and heat. A calm mental picture treats the star as an onion made of glowing shells rather than flesh. At the very centre, a compact fusion core works steadily. Around it, several broad layers carry energy outward by different methods. Near the core conditions favour convection. Convection is energy transport by rising hot fluid and sinking cooler fluid. The analogy is a pot of thick soup heated from below, where hot parcels slowly rise in columns, while cooler parcels slide downward between them. Inside Spica, these columns are not liquid in the usual sense, but ionized gas. They still follow the same rule. Hotter, lighter material tends to move upward, while heavier, cooler material tends to sink. This process mixes the core and spreads new elements through that region. Above the convective core lies a wide radiative envelope. In that envelope, energy moves not by bulk motion, but by the random flight of photons. Each photon is absorbed and re-emitted many times as it scatters through the dense gas. The process resembles light trying to escape a fog-filled hall with many thin curtains hung in layers. Every curtain lets some light through while sending some in new directions. Over time, the photons wander outward until they reach the photosphere and finally escape. The border between convective and radiative zones is not a sharp wall. It is a transition region where stability against rising parcels gradually increases and where waves can reflect and refract. Inside these layers, pressure waves travel through the star. They behave like sound in a solid yet move through hot plasma instead of rock. Some waves compress and expand material mostly in the radial direction. Others cause more sideways motion. Together, they form a subtle pattern of global oscillations. A signal would experience these oscillations as tiny periodic changes in brightness or line shape. For a star like Spica, such effects are delicate and require long, steady watching to detect. Intuition faces a limit here because as no direct view of the interior exists. All knowledge about these layers comes from models constrained by surface properties and by the general theory of stellar structure. The limit is one of observational access rather than of principle. Instruments cannot sample pressure and temperature at various depths. They can only receive light from the outermost layers. The onion interior must therefore be reconstructed from that outer skin and from the rules of physics. On small scales inside the core, forces act over short distances and times. The fusion reactions occur on lengths measured in fractions of the stellar radius, and on times measured in fractions of a second for individual interactions. On the scale of the full star, the energy generated in the core takes hundreds of thousands of years to diffuse outward through the radiative layers. On the still larger scale of the binary system, the interiors change only slowly over millions of years, while the orbit repeats every few days. That scale shift from short microscopic events to long macroscopic evolution allows the outer appearance of the star to remain steady, while countless interactions occur below. Radiation pressure plays a more important role here than in cooler stars. Radiation pressure is the push exerted by light when it is absorbed or reflected. In these hot interiors, the density of trapped photons is high, and their combined push adds significantly to gas pressure. The layers must then find a joint balance between gravity gas pressure and radiation pressure. In the mental onion picture, this means that each shell is supported partly by the restless motion of particles and partly by the streaming of photons. A useful visual anchor shows a vertical slice through the star with concentric bands of slightly different brightness. The central band glows fiercest, representing the fusion core. Above it, a broad band shines a little less intensely and symbolizes the radiative transport region. Farther out, another band softens again and marks the layers where gas begins to thin toward the photosphere. Each boundary is blurred like the gentle blending of colors in a long sunset sky. In reality, the composition also changes with depth. Near the center, fusion has already turned much of the original hydrogen into helium and other nuclei. Farther out, the material remains closer to its initial mix. Over the long life of the star, the convective core slowly pulls fresh hydrogen inward and delivers processed material outward, extending the main sequence lifetime while building up heavier elements in stages. Models that follow this evolution reveal another limit to everyday intuition. Such massive stars burn their fuel very quickly in absolute terms, yet still live for many millions of years. Their lives are long compared with human spans, but short compared with the age of the galaxy. For the current phase, Spica sits comfortably in a stable main sequence stage. Energy production, interior structure, and outer emission hold to a steady pattern. Small tidal distortions from the companion add only gentle corrections to the deep balance between gravity and pressure. The inner onion of hot shells therefore hums quietly beneath the visible surface, while the binary orbits in its curved spacetime well. From the steady interior, the flow of energy continues outward and sets the conditions that will later shape wind's mass loss and the future evolution of both stars in the sections to come. In a close binary of hot massive stars, even material that seems securely bound can slowly drift outward. The combination of intense radiation and tidal forces drives a long-term loss of mass from each component. This mass loss takes the form of a stellar wind, a continuous outflow of gas that escapes the gravitational grip and streams into surrounding space. The process is not explosive. It is more like a steady leak from a deep reservoir that never fully drains. In the case of Spica, characteristic wind speeds reach about 1,000 kilometers every second, comparable to circling a whole planet in a few minutes. That speed reflects how much energy each particle gains from radiation and thermal motion before it crosses the boundary where escape becomes easier than return. The physical detail at the heart of this mechanism lies in the upper layers of the atmosphere. Their atoms and ions absorb light in many narrow, spectral lines. Line driving is the push that photons exert when they are absorbed in these lines and transfer momentum to ions. A gentle analogy imagines countless tiny sails embedded in the gas. Each sail catches a small fraction of the outgoing light and feels a minuscule shove. Taken together, the shoves add up and accelerate the outer layers into a supersonic flow. At first, this wind rises almost straight outward from the surface. In a single isolated star, the flow would expand symmetrically in all directions and create a roughly spherical outflow. In a close binary, the situation becomes more intricate. The companion star and the shared orbit break the symmetry and force the wind to respond to changing gravity and radiation fields. In that environment, the outflow bends and forms spiral structures and compressed regions where streams from different directions meet. A slow mental camera can step back and look at the pair surrounded by a faint, uneven halo of gas. The halo is brighter along certain curves where the two winds collide and pile up. Farther away, the halo fades into a thin mist that blends with the interstellar medium. Intuition often imagines winds as sudden gusts that come and go. Here, the flow is nearly steady on orbital timescales, but accumulates its effects over millions of years. At any moment, the fraction of mass leaving the star is tiny compared with the total. Over long spans, the integrated loss can still reshape the structure and alter the future evolution. Observation of these winds meets limits set by resolution and sensitivity. The gas in the outflow is thin and spread over large volumes. It does not shine as brightly as the photosphere. Much of the evidence therefore comes indirectly from subtle features in ultraviolet and optical spectra. Certain absorption lines appear broadened and shifted in ways that signal fast-moving gas along the line of sight. In some cases, broad emission wings form as the wind scatters light in many directions. A signal would read these shapes as fingerprints of velocity and density in the flow. However, models must fill in the three-dimensional structure because current instruments cannot map the wind in full detail around Spica. The limit is not in the rules of physics, but in the reach of measurement. On small scales near the surface, the wind begins where radiation pressure overcomes local gravity by a small margin. At those layers, the gas has not yet reached its final speed. It still fills the complex pattern of tidal forces and rotation. Some streamlines are drawn toward the region between the stars where the combined radiation field is strongest. Others fan out toward the outer sides of the lobes. On a larger scale that spans several times the orbital separation, the wind from each star begins to overlap. At that distance, the two flows merge into a broad joint outflow that surrounds the whole binary like a moving shell. On an even larger scale, measured in light years, that joint flow becomes a tiny contribution to the broader pattern of gas drifting through the galactic neighborhood. This scale shift from surface layer to system halo to galactic background shows how a local process builds into a faint yet widespread imprint. The presence of a companion also affects angular momentum. As gas carries mass away, it also carries away rotational and orbital angular momentum. Depending on where the loss is strongest, the binary can gradually shrink or widen. In many models of close pairs, winds and tides together act like a slow break on the shared rotation and orbit. For Spica-like systems, the rates are gentle enough that orbits change only slightly over the main sequence lifetimes. Yet even slight changes can shift the conditions for later phases, including any future episodes of mass transfer or envelope expansion. Visually, it is helpful to picture the system as two bright lamps wrapped in a moving translucent scarf. The scarf billows outward folds where streams intersect, and thins into near invisibility at great distances. The lamps remain sharply defined points at the centre of this flow. Their light both reveals and drives the wind. Over time, the drifting gas may leave weak traces in nearby clouds, or add to the raw material for future generations of stars. In the present, however, the wind mainly serves as a quiet mediator between the hot surfaces and the cold surrounding space. It carries away heat mass and momentum in a continuous exchange that never disturbs the calm appearance of the point of light in Virgo. That gentle leaking of material prepares the stage for later evolutionary steps. Changes in the cores will eventually alter the winds and the shapes. Over time, those changes adjust the balance of the close binary pair. For intuition, this flow is challenging to picture, because it has no sharp outer edge or fixed, visible boundary. The wind does not form a crisp shell. It grades smoothly from dense inner layers into tenuous outer regions where individual particles drift almost alone. Any attempt to draw a simple boundary risks hiding that gradual change, so models use continuous profiles instead. These profiles describe how density and speed vary with distance and allow long-term effects on the orbit to be estimated calmly. Rotation inside the Spica system follows a quiet logic that ties spin to orbit. Over time, tidal forces gently adjust the spins of both stars until they nearly keep pace with their 4-day circuit. This state is called tidal synchronization, and it arises because gravity pulls more strongly on the near side of each star than on the far side. The unequal pull raises tidal bulges in the hot plasma, and those bulges do not always line up perfectly with the line joining the centers. When rotation runs ahead of the orbit, the bulge drifts slightly forward. When rotation lags, it drifts slightly backward. In both cases, gravity between the stars tugs on the displaced bulge and transfers angular momentum between spin and orbit. A simple image uses 2 large gear wheels immersed in very thick syrup. Each wheel carries a small raised ridge on its rim that stands for the tidal bulge. As the wheels turn past each other, the syrup resists motion, and the ridges push and pull on one another until their speeds slowly adjust. In the stars, the syrup is the internal friction of the plasma combined with radiative damping of tidal waves. The end result is similar. Rotation gradually settles close to a steady rate linked to the orbital period. In a system like Spica, the primary star likely spins once in about 1 day, roughly matching the daily cycle on Earth, but applied to a glowing sphere many times larger than the Sun. That rapid spin deepens the equatorial bulge and strengthens the contrast between pole and equator. A clear physical detail appears at the surface. The equator bows outward slightly farther than it would in a slowly rotating star, while the poles sit closer to the center. From some angles, this flattening is subtle. From others, the silhouette looks measurably squashed. A slow mental camera can stop the orbital motion and watch one star spinning alone. The central regions turn like a glowing oval disk, while thin lines of latitude sweep past in smooth arcs. Near the equator, features on the surface move fastest and trace long paths in a short time. Near the poles, motion is more modest and circles are smaller. This difference between equatorial and polar rotation speed is called differential rotation. Differential rotation is a pattern where different latitudes spin at different rates. The effect produces internal shear layers where faster moving gas slides past slower gas. Inside the star, those shear zones can stir material and reinforce mixing. They help bring new fuel into the core region and carry processed material outward. Over the long life of the star, this deep stirring affects how quickly hydrogen is used and how the core composition changes. Intuition meets a limit when trying to picture these flows in 3 dimensions. It is natural to imagine the star as a rigid globe spinning like a solid ball. In reality, the interior is more like a set of nested shells of fluid, each with its own slightly different speed. Observation faces a similar boundary. No direct measurement can watch the patterns of flow beneath the photosphere in a distant star. Information comes instead from line profiles in the spectrum and from small changes in those profiles over time. Rotational broadening spreads spectral lines into wider shapes because light arrives from surface patches with different projected speeds. A signal would analyze that broadening and infer an average rotation rate yet it cannot easily separate the full latitude pattern. On small scales near a particular point on the surface, the main influence on rotation is local pressure and the nearby tidal field. On the larger scale of the full star, the combined effect of many such points decides the global spin. On the still larger scale of the binary orbit, all that spin contributes to the total angular momentum budget. Over millions of years, exchange between spin and orbit can shrink or widen the separation by modest amounts. The scale shift from local shear zone to global orbit shows how small internal motions can slowly change external architecture. As the stars spin, internal gravity waves also carry angular momentum between layers. These waves are excited by tidal forcing and by motions at the boundaries between convective and radiative zones. Some waves travel inward and break like gentle surf on deeper layers where they deposit their carried momentum. Others travel outward and dissipate in the outer envelope. Together they form another quiet channel, through which rotation can even out or develop new gradients. Models that follow this process must rely on theory, because direct observation of such waves in Spica is beyond current capability. This limit is one of resolution in both time and sensitivity. The signals they produce in brightness and spectra are small and easily masked by other effects. In the mental picture of the two immersed gear wheels, these waves play the role of ripples in the syrup that transport the influence of one ridge to regions that do not touch it directly. Visually, the whole system can be pictured as two glowing ellipsoids, whose longest axes always point nearly toward each other. Each ellipsoid spins about its own centre, while both travel along the shared orbit. The surfaces slide past in a way that looks almost mechanical, yet remains fluid and continuous. There is no noise or jerking motion, only smooth repetition. Over long spans of time, the ongoing exchange of angular momentum will slowly shift the balance. If mass loss through winds removes more angular momentum from one star than the other, synchronization may be slightly offset and new tidal adjustments will begin. In the present era, Spica appears close to a steady compromise where spin and orbit are nearly locked. That quiet lock means the same faces tend to pass the line between the stars at similar points in each cycle. It also means that surface features influenced by tides can persist in roughly fixed locations. From the outside, this intricate play of spin and tide remains hidden within the single bright point of light. Inside the system, it forms a stable mechanical rhythm that helps set conditions for any later mass transfer events and for the eventual paths that both stars will follow as they move away from the main sequence in distant cosmic time. From far away in the galactic disk, Spica no longer looks like a detailed double system. It becomes part of a loose gathering of hot young stars that share a common origin. The pair belongs to a population that lights up its surroundings with intense ultraviolet radiation and strong stellar winds. These stars act as local architects of interstellar space, slowly reshaping the gas and dust around them. A useful way to picture this environment is as a dim room filled with faint smoke with several bright lamps gradually clearing a hollow around themselves. Each lamp eats into the haze, not by contact, but by steady light and warmth. In the region around Spica, the same kind of hollow forms in interstellar gas. Ultraviolet photons from the hot surfaces strip electrons from surrounding atoms and create a bubble of ionized material. The boundary of this bubble does not look sharp. It is a transition zone where fully ionized gas grades into partially ionized layers and then into cooler neutral material farther out. This boundary shows up as a subtle gradient in temperature and density rather than as a crisp shell. One rounded number gives a sense of scale. The ionized bubble can reach spans of several tens of light years, comparable to carving a clear sphere through a cloud the size of a small star cluster. Within that volume, the gas is warmer and more transparent to certain wavelengths. The visual anchor centers on a three-dimensional hollow, a softly glowing cavity suspended in darkness, with its inner walls traced by faint emission. Inside the cavity, the binary shines near one side like a bright knot off center rather than at the exact middle. That asymmetry reflects the fact that surrounding gas is not uniform. Some directions contain denser clumps that resist clearing, while others offer easier escape paths for radiation and wind. On small scales close to the stars, the interstellar medium is absent and only stellar winds and radiation dominate. On larger scales, the cleared bubble touches the surrounding molecular clouds and transmits pressure into them. Over even larger scales, those clouds sit as small features inside a spiral arm segment of the galaxy. This scale shift from cavity to cloud to spiral arm shows how energy from a single system spreads outward into the galactic environment. The influence of Spica and similar stars also extends through shock fronts. Where fast stellar wind meets slow ambient gas, a thin shell of compressed material forms. In this shell, temperature and density climb and cooling radiation escapes in characteristic lines. The shell does not stay perfectly smooth. It collects ripples and clumps as denser patches cool faster and lighter patches expand more. A mental camera can hold an edge on view of the cavity wall and see it as a gently wrinkled membrane. Bright knots mark denser spots, while darker gaps hint at regions where gas has already drained away. Intuition may expect that such influence would be easily visible as dramatic glowing arches. In reality, a clear view is hard to obtain. Observation meets limits set by line of sight, confusion and low surface brightness. Light from the cavity walls must compete with foreground and background emission from other gas along the same sightline. Instruments also have finite resolution and sensitivity. Faint gradients can drown in noise or blend with unrelated structures. The limit here is one of disentangling overlapping layers rather than a lack of any signal. A signal would probe this environment using specific emission lines that trace ionized gas. By measuring their strength and spread across the sky, it would map the outline of the bubble in projection. It would then compare the motion of gas in those lines with the expected expansion driven by winds and radiation pressure. From those comparisons, the age and energy input of the system could be inferred. Within this context, Spica's mass and brightness matter beyond its own interior. Massive hot stars live fast and end young on cosmic timescales. A typical lifetime for a star several times the Sun's mass may be only a few tens of millions of years, comparable to a short chapter in the long history of the galaxy. During that chapter, the star produces large amounts of ultraviolet light and heavy elements in its core. If the core eventually collapses in a supernova, those elements will be dispersed into the interstellar medium. Even before that endpoint, winds already carry processed material outward in smaller amounts. The region around the binary therefore acts as a staging ground for later enrichment. On dramatic scales, this flow feeds future generations of stars and planets, yet the process unfolds slowly and without sharp boundaries. From the perspective of the wider galaxy, Spica is one member of a larger association of hot stars that share similar ages and motions. Their combined influence shapes a patchy network of ionized bubbles and compressed cloud edges. Some edges may host triggered star formation, where external pressure nudges dense clumps into collapse. Others may simply drift and dissipate. The details depend on local conditions that models can only approximate. Intuition again faces a boundary because the distances, densities and timescales involved differ greatly from everyday experience. It is difficult to feel how a wind that thins to a whisper at many light years can still matter. Yet integrated over a few million years, that whisper carries enough momentum to carve cavities comparable in size to stellar nurseries. Visually, this larger context can be imagined as a wide slice through the galactic disk. The slice shows dim filaments of gas, darker knots of molecular clouds, and several pale bubbles where hot stars reside. Near one side of one bubble lies the tiny marker representing Spica itself, unresolved as a double in this broad view. From the inner scale of distorted photospheres to this outer scale of carved cavities, the same radiation and gravity work in different ways. They shape surfaces, winds, and finally the structure of interstellar gas. In the ongoing evolution of the binary, these environmental effects will frame the later stages, when the stars exhaust their core fuel and change character. The calm reshaping of nearby space that takes place now sets the initial conditions for that later transformation which unfolds on timescales that reach far beyond the brief rhythm of the current orbit. The bright double star in Virgo does not remain frozen in its present pattern forever. Its twin components follow a finite sequence of internal changes that gradually alters their size, luminosity, and interaction. The story of that evolution begins deep in the cores, where hydrogen fusion still proceeds steadily. For stars as massive and hot as these, that quiet burning stage lasts only on the order of 20 million years, roughly the length of a single short chapter, compared with the multi-billion-year history of the galactic disk around them. During this interval, the structure remains close to the layered pattern, already described with a convective core feeding on fresh hydrogen and a radiative envelope carrying energy outward. A calm image treats the core as a slowly rising mound of processed material surrounded by shells that keep adjusting to maintain balance between pressure and gravity. As hydrogen in the central region becomes depleted, the core contracts and heats, while the outer layers respond by expanding and cooling. In a single star, this change would inflate the envelope into a larger, more diffuse shape. In a close binary like Spica, the expansion pushes the surface closer to the Roche-Lobe boundary that encircles each star. At this distance, the teardrop form already nearly fills its gravitational hollow. Further swelling can bring the photosphere into contact with the narrow saddle between the lobes. The main physical detail becomes a gentle crossing of that saddle by gas. Material near the pointed inner tip no longer finds a restoring pull back toward its original host. Instead, it can drift along the lowest path in the combined potential and form a slow stream toward the companion. A helpful analogy sees this as a sand pile built on a very shallow ridge. Grains accumulate until the slope at the crest becomes too steep, then small slides begin to carry sand down into the neighbouring hollow. Nothing explosive happens at first. The flow stays narrow and continuous like a pale arch of mist stretched between two distant hills. In the real system, this arch is a curved stream of hot plasma that leaves one star near the inner Lagrange region and bends toward the other under gravity and orbital motion. On small scales near the stream, individual parcels of gas trace helical paths as they fall and wrap around the receiving star. On larger scales, the transfer reshapes the mass distribution of the binary and alters its orbit. If the more massive star gives mass to its companion, the mass ratio and separation can change in ways that reverse their roles. This process is called mass transfer. Mass transfer is the movement of stellar material from one component of a binary to the other through their shared gravitational saddle. Over time, it can strip the donor star's envelope and cause the accretor to swell and brighten. The details depend on how fast the transfer proceeds and how the received material spreads. Some flows may settle into a ring or thick belt around the gaining star before sinking inward. Others may plunge more directly into outer layers. Intuition meets a limit here because the future shapes and rates cannot be seen directly. They must be projected from models that weave together hydrodynamics, radiation rotation, and magnetic effects, each with uncertainties. Small changes in initial mass spin or wind strength can lead to different outcomes over millions of years. Observation faces a similar limit of timescale. The full story of envelope swelling and mass exchange unfolds so slowly that only a brief moment is visible in any current data. A signal would need to monitor many similar systems spread across the galaxy to reconstruct a statistical sequence rather than watch a single pair age in real time. As fuel runs low in the core and its composition shifts toward heavier elements, the internal structure changes again. The core contracts further and heats enough to ignite new fusion stages in a more compact central region, while the envelope responds with additional expansion or rearrangement. For a star of several solar masses, this chain of steps eventually leads to a compact core supported mainly by quantum pressure and thermal motion in very dense matter. When that support fails, the core can collapse in a brief event that releases enormous energy and throws outer layers into space. In calm language, that event is described as core collapse. Core collapse is a rapid inward fall of the central region once it can no longer resist gravity. The outer envelope responds by rushing outward in a wave of energy and newly forged elements. On the small scale near the collapsing core densities climb in fractions of a second to values utterly outside daily experience. On the scale of the whole star, the outward moving front sweeps through in minutes to hours. On the scale of the surrounding interstellar gas, the expanding shell takes tens of thousands of years to grow into a faded remnant. That scale shift from seconds to millennia connects the brief violent center to the drawn-out cooling of the ejected material. Even this late chapter is hard to map in detail for Spica. Models must estimate when each star will reach instability, whether one will collapse before the other, and how the binary orbit will react. The end products may be a neutron star paired with a massive companion, two compact remnants, or separately drifting objects if the explosion unbinds the system. Present observations cannot yet decide which precise path will occur. They constrain current masses, compositions, and rotation, while the rest of the line forward remains a family of possibilities. A mental camera can hold a very slow sequence in which the present bright pair gradually yields to a dimmer couple of compact points embedded inside a broad, expanding shell. The inner points might continue to orbit each other, tracing tighter loops in a deepened gravitational well, while the shell thins into a faint ring of enriched gas. Over still longer spans, that ring merges with the galactic medium, adding heavy elements to the raw material for new generations of stars. In that sense, the future of Spica closes one loop and opens many others. Its present form is a bridge phase between the original cloud that formed it and the later systems that will grow from its remnants. The calm light that now shines from Virgo comes from a stage that sits midway between birth and dissolution, quietly linking short orbital days to long galactic eras, and preparing the ground for the broader cycles explored in the following perspectives. Spica is not an isolated curiosity in the galaxy. It is one voice in a broad choir of massive close binaries that share similar inner rhythms. In the wider population of hot stars, systems with tight orbits and distorted shapes appear frequently rather than rarely. A helpful image treats the galactic disk as a vast orchestra. Individual stars become instruments and binaries become duets that play intertwined lines on the same stand. In that orchestra, Spica resembles a bright pair of brass instruments, loud and clear, yet still only one section among many. Statistical studies indicate that about 1 in 2 massive stars belongs to a close pair or higher, multiple similar to reaching into a large box of glowing beads and often drawing out 2 fused together instead of a single one. This simple number anchors the idea that systems like Spica are common builders of structure and heavy elements, rather than special exceptions. On small scales, each binary carries its own detailed architecture of masses, spins, and tidal distortions. On larger scales, many such systems together define the overall character of high-mass stellar populations in spiral arms. On the largest scales, their combined output of light and enriched gas helps shape how galaxies grow and shine over billions of years. The physical detail that links these levels is the way mass and energy leave each pair. Hot winds, later outbursts, and eventual core collapse events all contribute to the shared reservoir of interstellar gas. A calm visual anchor centers on a spiral arm segment seen from above. Along the arm lie clusters and loose groupings of blue-white points. Some appear single, others hide close binaries like Spica. Between the points, faint threads of gas and dust curl in lanes and filaments. In that scene, many duets play together, and their overlapping light fills the arm with a pale glow. Intuition might easily picture population statistics as abstract tables detached from concrete systems. Here the connection stays direct. Each entry in a distribution of masses and orbital periods stands for a real pair of distorted stars with gravity darkening on their surfaces, and winds that breathe into nearby space. Yet there is a clear limit to what can be known about the full ensemble. Observation faces incompleteness. Distant binaries that align nearly face-on may reveal almost no radial velocity change. Others hide in crowded regions where their light blends with neighbours. Some sit behind thick dust that dims their emission. As a result, catalogues miss a fraction of existing pairs and undercount the true numbers. The limit of observation here comes from distance and obscuration rather than from any gap in theory. A signal would try to correct for this by building models of detection efficiency and by comparing regions with different levels of crowding and dust. Even then, residual uncertainty remains. On a local scale around Spica, the immediate association of young hot stars forms one small sample of the broader population. On the scale of the galactic disk, multiple spiral arms host many such associations. On the still larger scale of nearby galaxies, these arms repeat in different arrangements, each carrying its own orchestra of duets. This stepwise scale shift makes it possible to treat Spica both as a specific object and as a representative case when thinking about cosmic demographics. In models of galactic evolution, massive binaries supply several key ingredients. They inject mechanical energy through winds and later explosions. They return heavy elements synthesized in their cores to the diffuse gas. They can also leave behind compact remnants in tight orbits that may spiral together under gravitational radiation in very distant futures. For now, Spica remains far from that stage. It sits in the long main sequence portion of its life. Still, the future paths explored earlier tie directly into these population roles. A single close pair may seed a thin shell of enriched gas. Many such shells from many pairs overlap and create patchy layers of heavier elements through the disk. Intuition often imagines enrichment as a smooth filling. In reality, it resembles overlapping ripples on a large pond, each ripple born from a specific event and fading while others join it. Spica's present state belongs to the early part of that ripple chain. Another quiet limit of intuition arises when considering time. The orbital period of about 4 days feels short compared with the age of the system. In 20 million years of main sequence life, the pair completes hundreds of millions of revolutions. On a human timescale, this would resemble a small wheel that spins many times each second, while the machine housing it changes shape only very slowly. The repetition erases the memory of individual cycles. Only long-term averages matter for the surrounding medium. From the perspective of the galactic disk, Spica's current chapter is therefore a brief recurring pattern folded into a much slower rearrangement of gas and stars. The galactic plane thickens and thins. Spiral arms wind and unwind. Star-forming regions ignite and fade. Through all this, generations of massive binaries rise and vanish, each adding their own contribution. Visually, a mental camera can zoom out until the double point of Spica blends into a continuous band of light encircling the sky of the galaxy itself. In that band, individual duets cannot be distinguished. Only the combined glow and chemical imprint remain. Within that smooth appearance lie countless close pairs whose inner gravitational hollows and distorted shapes mirror the structures already traced here. Spica's role in this ensemble is modest yet real. It demonstrates how a single compact system can join local galactic and even intergalactic cycles through steady radiation wind and eventual transformation, preparing the way for a final perspective that rests on the quiet continuity of these processes across cosmic distances and times. In the calm stretch of the Virgo sky, Spica marks both a place and a time. Its light travels across curved galactic space-time as a moving record of the system's changing life. Every photon that leaves the distorted surfaces carries information about conditions at that moment, then drifts outward along smooth geodesics through the Milky Way. Light travel time is the delay between emission and reception caused by the finite speed of light. For Spica, that delay is about 250 years, roughly comparable to a stack of human generations reaching back to the age of simple mechanical clocks. The system seen at this distance is therefore not in its current state, but in the state it held centuries earlier along its world line. A world line is the path an object traces through space-time. In imagination, that path becomes a long, gently curving thread running through a 4-dimensional volume, with each point on the thread marking a specific event in the life of the binary. At any instant, a thin fan of light spreads out from the thread and moves into the surrounding darkness. A helpful visual anchor treats those light fans as translucent ribbons flowing away from a slowly circling pair. Each ribbon marks one orbital phase, then fades as it drifts outward and mixes with older emission. On small scales near the stars, the ribbons lie close together, separated by only a few orbital periods in proper time. On larger scales, they spread apart into a loose stack that fills a corridor hundreds of light years long. On still larger scales, the corridor becomes one narrow strand in a vast web of light crossing the galactic disk. This scale shift from local arc to corridor to web links the nightly steady point in Virgo with the broader transport of energy across the galaxy. Spica sits in a curved potential well, set by both its own mass and the surrounding distribution of stars and dark matter. The binary orbits within that well, while the galaxy as a whole spins slowly around its centre. Over roughly 200 million years, a star near the Sun's distance completes one circuit, a period comparable to a single long season in the life of the galactic disk. During a single galactic orbit, Spica cycles through many phases. Its inner structure evolves. Its winds carve changing cavities. Its eventual transformations send new shells of enriched gas outward. Yet at any given distance, only one thin shell of its history passes by at a time. The analogy of a quiet river helps. Imagine a smooth channel where layers of water slide past each other at slightly different speeds. Each layer carries fallen leaves from a different moment upstream. At a fixed rock on the bank, only one thin layer touches the stone at once, holding only the leaves from a particular interval. In the same way, a given point in space sees only the light from one period in Spica's life at each moment. Older phases have already flowed past. Later phases have not yet arrived. Intuition meets a limit when trying to hold all these layers together. Everyday experience offers no direct sense of hundreds of light years or hundreds of millions of years. Distances on a planet's surface feel large, yet still allow a journey across continents within days. If a vehicle tried to reach Spica at highway speed and never stopped, it would need a span of time many trillions of years long, far exceeding the age of the galaxy. That contrast between travel time and light time illustrates how extreme the separation is. Even so, on cosmic scales, Spica lies in a near neighbourhood, rather than in a remote frontier. Observation of its motion and structure also encounters limits set by geometry and resolution. In 3 dimensions, the system follows a gentle orbit around the galactic centre, while participating in small vertical oscillations above and below the midplane. A signal would try to reconstruct this path from tiny shifts in position and gentle drifts in spectral lines over time. These effects appear as minute angular displacements and subtle velocity components along the line of sight. The limit arises because angles become extremely small at hundreds of light years. Even a sizable transverse speed produces only tiny changes in apparent position across decades. Instruments can measure these changes only down to a certain threshold. Below that threshold, different possible paths through space-time fit the same limited data. Models then supply the missing detail, but with associated uncertainty. A calm mental image places the Milky Way as a great disk of light, then draws a thin, transparent tube that encircles the galactic centre. Within that tube, a narrow ribbon marks Spica's world line as it advances on its slow circuit. Around the ribbon sit many similar paths traced by neighbouring stars woven together like strands in a wide, delicate fabric. Each strand emits its own stream of light, and the streams cross and blend without colliding as they move through the disk. To any point embedded in this fabric, the sky appears as a dome filled with bright knots and faint haze. Among those knots, Spica shines as one distinct point whose light encodes both distance and gravitational environment. From the perspective of the binary itself, proper time passes according to the local metric set by its mass and by the galactic field. Proper time is the time measured along an object's own world line. The difference between that time and coordinate time in a chosen frame stays small for these moderate fields, but is still real. At this gentle level, relativity does not twist the system into extreme forms, yet it quietly shapes every orbit and every path of light. Even when distortions of spacetime remain mild, they determine which geodesics light can follow, and which orbital configurations remain stable. In this sense, the curved geometry under Spica acts like a softly shaped basin in which the binary moves. For vast periods, the system traces nearly repeating loops inside this basin. Later, when internal evolution alters its mass distribution or sends shockwaves into space, the world line bends into new forms. The basin stays while the path within it changes. One final visual anchor sees the whole scene as a large dark amphitheatre whose floor is gently concave. Tiny bright dancers glide in slow ellipses across the surface, each leaving faint trails that persist only in thought. Spica is one pair of dancers moving close together, their shared trail slightly warped by their mutual pull and by the general curve of the floor. Around and far beyond them, many others follow their own turns. Nothing breaks the calm. Motions remain smooth, governed by the same simple rules, from the near scale of the distorted photospheres to the far sweep of the galactic orbit. The system rests within a continuous geometry. That unbroken context prepares a natural step toward a final, quieter view, in which Spica becomes part of a larger background of steady light and slow cycles, against which rest can settle more deeply and thoughts can drift more freely into silence. In the wide structure of the galaxy, the Spica system now settles into a quiet role. Its light and gravity and slow internal changes continue without haste or interruption. Nothing sudden announces each new orbit. The pair simply turns again and again inside its shared gravitational hollow. Close to the stars, the distorted photospheres keep their teardrop forms with darkened equators and brightened poles, tracing the influence of rapid spin and deep potential. Each rotation smooths out short-lived disturbances in the outer layers. Density waves wash through the atmosphere like gentle ripples crossing a broad lake and fade before they can leave lasting scars. On scales of minutes and hours, convection cells rise and sink inside the core, while energy flows outward through the radiative envelope. On scales of days, the orbital motion carries the stars through all alignments, bringing moments of slight eclipse and moments of side-by-side brightness. On scales of millions of years, nuclear reactions steadily convert light elements into heavier ones in the interior. The difference between these clocks becomes a central feature of the system. Fast and slow processes coexist and overlay each other. Together they form a layered rhythm that never repeats in quite the same way, yet always stays within narrow bounds. A helpful analogy imagines a calm bay at the edge of a great ocean. Small surface waves pass in minutes. Regular tides rise and fall over half a day. Long swells from distant storms arrive only after many days of travel. At any instant, the water level and motion reflect all of these patterns at once. In a similar way, the present state of Spica combines rapid oscillations in its atmosphere and steady orbital cycling. It also contains very slow structural evolution in the core. The main physical details remain anchored in the same features already traced. There is the compact separation compared with stellar size. There is the elongated shape of each component. There is the slight offset between the center of mass of each star and the deepest point of its gravitational hollow. Each of these features feeds into observable signatures in light and line profiles, and together they define the system more reliably than any single number. From a vantage just outside the binary, the visual anchor is simple. Two blue-white stars spin in a tight dance seen against the dark texture of interstellar space. Their mutual pull stretches them slightly toward each other. Between them, the shared potential basin dips like a shallow valley floor. Radiation pours outward in all directions, softening the outlines of nearby dust and gas. Further away, the influence becomes more diffuse. The ionized cavity carved by winds and ultraviolet light continues to expand at a slow pace, its inner wall glowing faintly where electrons recombine with ions. Beyond that wall, neutral clouds drift only gradually altered by the pressure and momentum of the expanding shell. On still larger scales, the spiral arm that hosts Spica rotates around the galactic center. It carries the system through regions with slightly different densities and tidal fields. In this scale shift, the binary's specific details blur into broader statistical patterns, yet they never vanish entirely. They remain encoded in the chemical composition of the gas. The system will eventually return, and in the subtle kinematic imprint it leaves on surrounding material. There is a clear limit to what any outside measurement can reconstruct about this layered story. Observation meets boundaries set by distance and brightness contrast and intervening material. Some quantities, such as the internal mixing rates in the core, or small variations in envelope opacity, cannot be measured directly at all. They must be inferred from simplified models and from comparisons with other systems at different stages. The limit here is one of resolution in both space and time. Data samples only a few phases of a very long evolution and only along one sightline through one galaxy. Intuition also meets its own boundary. Concepts like curved gravitational potential surfaces and overlapping timescales from hours to millions of years lie far from familiar experience. Cavities tens of light years across also lie outside everyday intuition. To handle them, the mind compresses distances and durations into compact images, like diagrams or gentle analogies. Those simplifications are helpful but incomplete. The real system is more intricate and quiet than any single image can express, yet that intricacy remains stable and predictable on short observational scales. Over centuries, the 4-day orbit stays almost unchanged. Over the same span, the spectral type shifts only slightly, and the ionized bubble grows by a modest fraction of its size. From that perspective, Spica functions as a steady reference, a calm marker of structure and scale in Virgo. A last wide visual anchor holds the Milky Way seen edge-on in dark space. The disk appears as a pale thin band crossed by dust lanes and dotted with brighter knots. Within one small knot lies the association that includes Spica. Within that association lies the close pair itself. Its distorted surfaces and tight orbit now feel like a fine detail etched into a much larger plate. The same basic forces that shape this detail also govern the entire scene. Gravity draws matter together, pressure pushes back, radiation carries energy outward. Time stretches these interactions across ranges from minutes in a stellar atmosphere to hundreds of millions of years in stellar populations. In this broad view, nothing urgent occurs. The binary continues to turn and to radiate and to evolve at its own deliberate pace. Its future holds changes in composition and structure and possible episodes of mass transfer. It also holds eventual transformation into compact remnants and expanding shells. All of these stages remain governed by the same quiet rules already at work now. The present moment in the life of Spica is therefore not an isolated point. It belongs to a smooth segment in a long continuous curve. That curve joins the collapse of the original cloud to the later dispersal of enriched gas. It links local distortions of space-time near the photospheres to the gentle galactic potential that guides the whole orbit. Within that continuity, the system provides a stable, distant pattern of light and motion. It rests in its place inside the Virgo star field and inside the galactic disk. The orbit holds, the internal balance holds. Surrounding structures shift only very slowly around it. In that slow, shifting cycles of light and gravity repeat until awareness of detail gradually loosens and drifts into quieter and more restful lot. What can I say?